Hello. Pops just became public recently, and it can probably be rather overwhelming if you don't have an extensive background in vector algebra and graphics and shading. I'm going to attempt to walk you through how I built this sort of rock, paper, scissors simulation from scratch using Pops. Most importantly, I want to explain to you how I think about attributes, which is basically the thing that makes Pops work so well. If you just want this file that you're seeing in front of you, then you can feel free to download it on my Patreon, which I am now starting to use because everyone in the TouchDesigner community seems to have a Patreon these days. If you want to follow me through this tutorial and learn how to build this kind of network from scratch, by the end of this video, we will have a fairly similar network to what you're seeing here. There might be some slight differences. Let's get started by building this network from scratch. So we're here in a brand new network, and the first thing I'm going to do is I will put down from the pops menu a point pop. Now, a point pop has some information which looks really similar to the information that we used to get when we put down a SOP. For example, this box SOP, if I look at its information, has 24 points, some primitives and polygons. SOPs have always had these attributes, but I don't think they were super common to use in a lot of lower level projects. But those attributes are basically what make pops so efficient. And it's really important to think about building our project in a way that we can best make use of these point attributes. What I've done here is just created a single point, and I'm pulling up that window by just middle clicking. There's one single point here made from this point pop. And a great operator I can use to just randomly generate a bunch of points is the random pop. With the random pop, I can go up here to the top of the parameters box, and where it says extra points per source point, I'm just going to say, give me 50 extra points. Now, if I zoom in here and put the viewer active, all of those points are all being generated up here in the very first quadrant. Basically, the points all have X, Z, and Y values going from 0 to 1. Now, for my case of rock, paper, scissors, since it's just going to be on a flat screen, I really don't need this Z axis at all. And here's where we're going to start making use of the first attribute in pops, the P, or the position attribute. What I can do, instead of using P, which is a collection of 3 different floats, the X, the Y, the Z values, if I just put in parentheses here, only 0 and 1, and press enter, well, now I'm only setting these points to be randomized, their position on the X and Y axes. So you can see now they don't go forward in the Z direction. Because this will become useful later, I'm going to have their positions be from -1 to 1, which means that they now show up in all 4 of these quadrants on the XY plane. Because my final output is also going to be in vertical aspect ratio, I'm going to use a different operator for the Y direction. I'm only going to have the X values go from -1 to 1. Right now, the Y and the Z aren't doing anything. The points are just scattered along the X-axis. Out of this random pop, I'm going to connect it to another random pop. And this random pop, I'm going to tell it to only set the points along the y-axis. And this time, because the aspect ratio for vertical is 1.77, I'm going to have the points go from -1.77 to +1.77. Now, here's the first kind of weird thing I've discovered with pops. I don't have a good explanation for why this is the way that it is, but basically, when we generate randomness, we always use something like a seed, right? And everyone knows how seeds work. Like you change the seed and then it makes things random. If the seed of random 1 and random 2 are the same seed, they tend to follow a very obvious pattern of generation. We could try to use different types here, like say directional or exponential or Cauchy Lorentz, whatever that is. Um, but as you can tell, they all kind of follow a recognizable pattern. So the only solution I've really found to make these truly random is to set the seed here to always be different from whatever the seed is on the other random. In this case, I'll just make random 2 the seed 2. So that way these points are all completely scattered in vertical aspect ratio. All right, so next I could just continue building the network the way that you saw in the beginning of the video, and I can show you where every single operator is supposed to go. But that's not a realistic way of developing because it's an iterative process and you don't always know what operators you're going to need. And you kind of need to learn how to solve problems as they arise. So, to make the network more understandable, I'm going to skip over the whole feedback section and I'm just going to start making something visual that I can show on the screen. That way we can see stuff moving around while we're learning how it works. So I'm going to connect this random out to a null pop all the way over here. I'm just going to rename this guy to end, meaning it's going to be the end of the pop network. I'm going to connect it to a geometry, and we're going to make a render network the way that we always do in TouchDesigner, which is that we throw down a camera and a render top. Now, if I turn the display flag on for this render top, or if I press D on it, you'll probably see that the points are very, very dim and hard to recognize. So one thing I can do is I can use a material, like a point sprite material, put that on the pops geo, and then raise the constant point size to something bigger so that they can more easily be seen. But now you probably can recognize that some of the points are going off the screen, like this pop is cutting out of the frame. The reason for that is because the pops are being generated in vertical aspect ratio, but by default, this render is in horizontal aspect ratio. We can see that if I right click and go to info, it's 1280 by 720, 720p. It's also sometimes called 16 by 9 aspect ratio, or like I used earlier, it's 1.77 to 1 aspect ratio. What I'm going to do to fix that is I'm going to make it vertical. So the width here should only be 720 pixels, and the height should be 1280 pixels. Now, just for the sake of development, I think it would also be useful if there was a bounding box here. So I'm going to go to the old school SOP list. We'll grab a rectangle, connect that rectangle to a geometry, and great, we've got a square here. It's much smaller than our pop area. So let's fix the height of it. The height should be 1.77, right? But because the height is really only half of this number in the up and half of the number in the down directions, we take that number and we multiply it by 2. So the end result here is like 3.54. And it's going to be the same thing for the width, 1 times 2. So now what I can do is I can put a line material on this big ugly black box that we've got here. And now I can just see a nice, easy to understand bounding box of where all the pops should lie whenever they're made. I think this is good just to have on screen so we can understand what we're building. Next, we want these pops to start moving. So they've got an attribute for their position. What we need to make them move is a velocity. And if you're not familiar with vector algebra, I'll just kind of quickly walk through it here. The position in the future is just whatever your position is now plus whatever your velocity is now. So we can think about that as an attribute for velocity. To create a new attribute over here in the kind of setup area of our network, I'm going to right click the output of random2. I'm going to put down an attribute pop, and I'm going to declare a new attribute called vel for velocity. Our positions, there's 3 of them. There's an X, there's a Y, there's a Z. The velocity, we only need to go in the X and Y directions. So our velocity is just going to be a collection of 2 floats that by default are 0, 0. If I right click the output of this attribute pop and go to the pop to dat down here, I'll see all of the attributes from all of these pops. They're X, Y, and Z positions, which are always going to be 0. And they've also got a velocity in the X and a velocity in the Y, which is currently 0 by default. Now, let's say I want to make them move in some random direction. I could probably make use of the random pop again for this case. So I'll put down the random pop. And what I'm going to do is I'll say, instead of making the positions random like I've been doing before, I'm going to just get rid of that. I can go over here to this little play button that shows me all of the existing attributes in this pop, and I'm going to choose vel for velocity. And I'm going to say that the velocities can be somewhere between negative 0.01 to 0.01. I'm choosing really small numbers because I know from experience that when they're very large numbers, the points are all just going to shoot out of the screen really fast and you're not going to be able to see anything. If they're small numbers, you'll at least be able to see the movement a little bit as they make their way out of the screen. So if I take this pop to dat and just copy and paste it over here and look at it from this random pop, now I can see all the velocities are in some random direction as opposed to a second ago when the velocities were all 0. Don't need that anymore. Cool. Every pop has a position and a velocity. That means we are ready for a feedback loop. Feedbacks are like the lifeblood of TouchDesigner, so we're going to make them as is traditional. We will put down a feedback pop. We will put down a keyboard in chop, which will turn on whenever I press the number 1 on my keyboard. And I will link that to the start of this feedback as so. So whenever I press 1, these points are initialized, basically. Now, they're not moving yet. The reason they're not moving yet is because, well, the feedback needs to usually be looking at something. So I can take the end and I can drop it on top of the feedback the same way I would do with a feedback top. But they're still not moving. They're not moving yet because I haven't done anything to say, do this operation, make the position equal to the position plus the velocity. So the way we do that is we think about these attributes in terms of letters. Let's just say that this first attribute here is A, and this second attribute over here is B. Okay, there is an operator that we use if we right-click the output of feedback. It's probably going to be the most commonly used pop, in my opinion, the math mix pop. The math mix pop can be a little overwhelming when you first look at it, but it's basically got all these operations that you can do between the pop's attributes. So in our case, we want to take attribute 1 and add it to attribute 2. So we'll just use the A plus B operation. And we're going to say that the output is going to be the position, or P, right? From the drop-down menu, we should see P here. And we see all the other attributes we also have. Now, the position, again, we're only working in X and Y, so we'll be more specific here. We'll say that the position 0 and 1 are going to be the result of A which is the current position, but again, only positions 0 and 1. A plus B. B is our velocity. Our velocity is already just a set of two floats. So we don't even really need to specify 0 and 1, but we can if we want to. We can be really, really explicit here and say vel 0, 1. But before I even finished typing that, you probably already noticed that the points shot out of the screen. So great. This is where I can start spamming my 1 on my keyboard, and I can keep on resetting this. And you can see that this is how the feedback is working. Every single frame here, if I pause and go forward 1 frame, they start to move continually in the direction where their velocity is pointing. So over many frames, over a certain amount of time, it basically equates to movement. So our network can basically be split into 3 sections right now. If I right click, go to add comment and add an annotate box, I'll make an annotate over this section of the network that shows that this is for the setup. This area of the network, which is basically just going to be the feedback loop. We'll just make some space there. And then finally, the part on the right side, which is just our render setup. So I'll make that a little bit bigger, try and put all of these operators in so that the network's nice and tidy. Now, there is a bug in the experimental release in the current version where if you want to color these annotates, like for example, I would normally try to color a setup green, but every single color is magenta for some reason. So whether I pick green or blue or orange, they're always magenta, but that's okay. It's already a known issue and will be fixed in the future. So now what I want to do is I want to check if these points hit the edge of this bounding box, they should flip their direction that they're moving so that they don't continue to go outside forever. I want to keep them inside of this bounding box so that they're always just bouncing around. There's a lot of different ways to do this, but the most common one that I've seen other creators use is if you already know the bounds of your box. For example, in our case, we know that this box here goes from -1 to 1 in the x direction, and it goes to 1.77 in the y direction and -1.77. So those numbers basically come from here, the random, where we set the points to be between -1 and 1, and where we set their y positions to be between -1.77 and 1.77. So what we're going to do is we'll use another math mix here. With this math mix, we're just going to verify that our attribute, the position, is between 2 known things. A should be between B and C. So I'm going to choose that operation. What is A? A is going to be our position in X. And we know that in X, it should go from -1 to 1. B is the lower side, C is the greater side. So over here, from this random 1, we can just take whatever that value was, copy it, and paste it here as a reference for the lower bounds. So in case that number changes, maybe they spawn all the way up to -1.5, then here the bounding box can compare their X position with that continuously updating position. But for now, I'm just going to leave it as -1. We'll do the same thing with the greater side, the right side, the large number. I will copy that, come down here to attribute C, and I will paste that as a reference as well. Now, what we're going to do is we're not going to say that the position is the result of this, right? This is a logic statement that is basically just going to evaluate to true or false. Is A between those two numbers? It's either a yes or a no. So a more appropriate attribute in this case would be something like it is inside in the x direction. That's really all we need to keep track of. We're going to do the same thing for y, and we'll just add another operation down here. We'll do another is a between b and c. This time we're going to check is p1, is the y position in here between negative 1.77. This can be a reference, or the bigger 1.77. You can, of course, type that in as well if you want, but in my case, I'm just going to use a reference. Cool. If the y position is between the low and the high, then we will say that it is inside the y bounds. You may have to do this like 100 times while working on your network, but whenever you add new attributes and stuff like that, just press 1 to kind of pulse that feedback loop, just to make sure that all the pops recognize the new attribute that you just created. In my case, I made 2 new attributes, one called inside x and one called inside y. So if I connect this guy to a pop2dat, I should see positions are here, the velocities are here. They're not ever really changing. And I've also got my 2 extra tabs for is the point inside the y bounds and is it inside the x bounds. Eventually they all fly out, they all become 0. But for right now, we seem to be doing okay. Next, what we're going to do is we're going to say if that point is outside of the acceptable bounds, well, it needs to ping pong back inwards. So if it is too far outside of the y bounds, its y velocity needs to be flipped. And if it's too far outside of the x bounds, its x velocity needs to be flipped. And here's a way that we can do that. First, let's just, we could use another math mix, or we could do it in the same math mix. I think it doesn't hurt to do it in the same math mix, so why not? We're going to say that the current velocity is going to be inverted. Another way to think about that is we could basically say if our velocity in the x direction is currently 3.01, we need to make that velocity in the x direction negative 3.01. How do we invert it? Unfortunately, there's no operation, at least that I'm aware of. Maybe it exists here, and maybe I just have no idea. But there's none that just says like a is equal to negative a. But one operation you can use is a times b. If we think about that, a times negative 1, if negative 1 was b, that gives us this new a down here. So we're just going to make use of that operation. We're going to say a times b, the velocity in the x direction times negative 1 is going to give us a new attribute, which we will just call inverted velocity. Now, before I press enter, you might think to do inverted velocity 0 or something like that to be really specific, right? If I do that, unfortunately, it throws an error, and it says that this attribute inverted velocity was not found and needs to be created. So basically what that kind of means is over here where we explicitly declare an attribute and we say that it is a collection of 2 floats, or for example, 3 floats or 4 floats, it doesn't really do that automatically sometimes in these feedback loops. So one way to deal with this is we could make the inverted velocity over here in the attribute create so that we know that we're going to have it in the future. or whenever we create them here, we just need to make sure we're using the exact number of dimensions so that it can create it in this feedback loop. Take a look when I look at the information here. The point attributes that currently exist are just point, inside x, inside y, velocity. This inverted velocity doesn't exist yet. If I get rid of the 0 and press enter, the error goes away. Now there is an attribute for inverted velocity, and it is just a single float. It is not really a collection of inverted velocity 0, 1s, or 2s. So that's just something to keep a mental note of. And sometimes it's also worth it to just reset your feedback loop a couple times so that it can make all these attributes. But anyways, to not confuse you too much, our velocity x times -1 is now our inverted velocity. And you know what? Let's be more specific. Let's just call that our inverted velocity x. And I will, because now I have an inverted velocity and an inverted velocity x, I'm going to just reset the feedback loop a couple times, and that will refresh it. So now I only have the inverted velocity that I'm looking for. I don't have that extra data. So now we'll do the same thing for y, right? The a times b operation will say that whatever the velocity is in the y direction times -1 now becomes our inverted velocity y. And great, now we've got 2 extra attributes here that we can use if we want. So let's use them. Let's make another math mix just so that we don't have such a long chain of math mix operations. We'll use another one here. And the point of this math mix will be for velocity inflection. So we're going to say a conditional statement here. We're going to say if the point is inside of the x value, it's good. Let it keep on following its current velocity. But if it's not inside of x, or sometimes we would call that else, if it's not inside the x bounds, then we'll flip the direction. So that's this A if C else B. We kind of start from the result, right? The result is that its velocity in the x direction will be, by default, it's going to be A if C is true. So I guess let's start with C. What are we going to check? We're going to check if it is inside of x. Okay, if it's inside of x, then it should do A. If it's inside x, the velocity should just be whatever the, sorry, my caps lock is on. It should be whatever the velocity in the x direction currently is. But if it's not inside x, then we will say that the velocity in the x direction should be the inverted velocity x. Okay. And this is where we can give the feedback a quick pulse. And we can see that our points are now starting to bounce around whenever they hit that x boundary. Great. I hope you're still following, because we're going to do it one more time for y. We're going to do A if C else B. We'll say that the velocity in the y direction, if it is inside y, should continue to be the velocity in the y direction. Otherwise, we invert the velocity y. And I'll pulse it again. And just like that, we've got a bunch of points that continually bounce around in this rigid bounding box. So that's great. We can now take our camera for rendering over here. I'll zoom it in a little bit closer now that I know the points won't be flying outwards so much. And then even if I wanted to extend, say, the bounding box, we can do this. We can go to the x values, and let's say that maybe they can go a little bit further than -1. Maybe they can go all the way to -1.2. Now we've got some points over here that fly all the way to the edge of the screen, but they don't do it on the right side, because the right side should also be going all the way up to 1.2, right? There we go. So now we can adjust these bounds, but of course, as these bounds are adjusted, we should also adjust the bounding box of the rectangle. So now it would be 1.2 in both of those x directions. And now we should be able to see a little bit more precise of a visual. So this is totally up to you. You can be creative with this and design it however you like. But for the sake of this tutorial, I'm just going to leave it at -1 and 1 so that it's very easy to recognize. But now we've got some points that are kind of stuck out here in limbo. They are outside of the bounding box and the limits have been changed, so we'll need to reset to put them all back within the regular spawning boundaries. Okay, now let's try something a little more challenging. So originally when building this network, I kind of did it backwards. What I did is I created an attribute for the state. The state would be if, one of the points was supposed to be rock, or if it was paper or scissors. I created an attribute that I would constantly have to read from this table. So I would always need to keep an eye on the table and see if something was a 0, then I would make a mental note that it was paper. If it was a 1, then I'd make a note that it was scissors, or 2, it would be a rock. But that made development a little bit challenging. So what I'm going to suggest this time around is we actually focus on making the render part first so that it can be easier to kind of look at on screen what is happening. So to kind of prep for that, first what I'll do is I'll make a brand new attribute. I could do it in the same attribute over here, but why not just make use of more pops, because that can be fun practice, I guess. So anyways, I'll make a new attribute over here, and this attribute, we'll just call it the state. Now the state is going to be an integer because I only want it to be 0 or 1 or 2. I don't really want it to be a random number in between, like 1.5. So if we now have the state attribute and we move this pop to dad over here and take a look, we've got another column for the attribute state, and they're all 0 by default. If I change this to 1, then they're all 1 by default. So I'm just going to make it 0. Now I want all of those to be random. So this would be another great chance to use the random pop. We'll take a look at the scope for state, and state will have it be some value between 0 and 2. So now if I bring that over here, I can see that all of the states are currently 0 and 1. So it looks like it's not inclusive to 2. So I'll make it go from 0 to 3. Now all the states are sort of random here between 2, 0, 1, 1, 2, 0. Okay, so that's going to represent all of our rocks, papers, and scissors. That's great because when I refresh the feedback loop here, then that state is going to flow on through this network, and it's going to come all the way here to the end. Now what I want to do is I want to make a texture instancing network. There are probably a lot of tutorials that might do a better job of explaining it than me, but here's how I will try my best to explain it. First of all, we make a base. This base is where we're going to get the textures that we're going to render. So I'll just call it textures. In that base, there's basically only 3 textures we're going to use. I'm just going to quickly copy and paste those over. And I've got a texture for paper, scissors, and rock. Now, if you already have some textures you want to use, you can go ahead and grab them with the movie file in. You can do whatever you need to do to fit them to a perfect square. Maybe you need to scale them. I don't know, perhaps you also need to color them for some reason and make them green. I don't know, whichever textures you want to use. But just get them into like a nice square format. And then make sure that they all have basically the same name with a number at the end. So in my case, I've got fit, 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 fit 1, fit 2, and fit 3. So the only difference between these guys is the number at the end is 1, 2, and 3. Next, if I'm being completely honest, I don't really know how to do it using a point sprite material on the pops. So for texture instancing, the way that we used to do it in the past is we would just use something like a grid or a rectangle. I'll just use a rectangle and I will connect that rectangle to the geometry that I wish to render. So in this case, I'm gonna maybe move this geometry down, move this render down, move the textures in camera up, put this geo into here, this rectangle here, and I'm going to just turn rendering off for this geo with the little purple flag. Now in this geo up here, I'm going to turn instancing on. From this pop, I'm going to use this pop to determine the translation positions. The positions in the x direction would be P0, the positions in y would be P1, and of course, all of these points are way, way, way too big. So I'm going to shrink their size down to maybe just maybe like 0.2 or something. And then I need a material for this guy. In this case, I'll use a constant material on Geo3. Now, to instance all of these textures, what I can do is from the end pop, I can connect that to a chop using a pop to chop. The pop to chop will tell me information that I don't really need, like the position. All I need is just the state data. So position, I'm going to delete that. And here I have all 50 states of the pops that are floating around. They are either 2 or 1 or 0. And with this state information over here in Geo3, when I go to the second instancing tab, I can reference this textures base, textures slash the name of the operator inside of textures, which is going to be fit, and then a star representing that the number at the end is going to change based on whatever the state data is. So I'm referencing fit, and then to figure out which texture I should use, I'll drag and drop pop23 as the reference operator, and then the index itself will be chosen using the state attribute. So now I should see that basically for every pop that's floating around here that has a state of 0, it's going to have the paper texture. And same thing with scissors, same thing with rock. One thing you might notice is that if I pause right here, sometimes the textures, because they have transparent backgrounds, when one texture is on top of another texture, it kind of cuts out the one behind it. So to fix that in the constant, I'll go to the Common tab. I will turn Blending Transparency on, and I don't have a good answer for why we do this, but the source color is going to be source alpha, and the destination color is going to be 1 minus the source alpha. And then when I let it play, now there should be hopefully no issues with textures cutting out the textures behind them or any of those weird artifacts. So those are just the settings for transparent textures on top of each other. Okay, cool. So we've switched to basically a SOP-based rendering network here. There's probably a way to do it with point sprites. I just couldn't really figure out how to change the color map to be based on whatever the texture index is. But if anyone knows, feel free to share that information with me. That'd be super cool. So now that we've got some visual representation here of what the pops are as they're moving around, let's focus on trying to figure out when they have collided or when they have bumped into each other. Now is probably a really good time to give your project a quick save if you've been following along and building it from scratch by hand. We don't want to lose any of our progress so far. So give your project a quick save and let's continue. To detect collisions, I was, for some reason, under the impression that there was going to be a collision pop here. And maybe that's still in the works. But currently, what it seems like is the neighbor pop is what we use to measure or detect collisions. So the neighbor pop is really useful. We just plug it into our regular network like any other pop, and the neighbor can tell you by default the 5 nearest neighbors. If we drag this pop to dat over here and look at that neighbor, it will tell us these 5 new attributes for neighbor 0, 1, 2, 3, and 4. Now, when we're looking at neighbors, I would like for it to tell me the neighbors within this maximum neighbors distance, and I want it to tell me them in the order of the closest neighbor. And you'll notice a lot of the neighbors have this really, really high ID of like 4,294,000,000. That just basically is the default ID assigned to it when it wasn't able to detect a neighbor. So we'll just pretend that that number represents that no neighbor was found, and any number that is smaller than that is the ID of our closest neighbor. Now, when detecting a collision, we're really only interested in one neighbor, our one closest neighbor. So to get rid of all of those unnecessary neighbor 1, 2, 3s, and 4s, I'm just setting the max neighbors down to 1. We also aren't interested in the number of neighbors that we have because we know that there's only one that we're ever really checking for. So this column is now unnecessary. I will just reset the feedback loop by pressing 1, and boom, that column has been deleted because it's not really in use. Here's probably one of the coolest things about finding your neighbors is that you can also grab your neighbor's point attributes. So what I would like to know if I'm scissors and colliding with a neighbor is what are they? Are they scissors? Are they paper? Are they rock? So from my neighbor, I'm going to look for my neighbor's state attribute. And then I've got a column here that tells me my neighbor's state and if it's a 0 or a 1 or a 2, which is really useful. So now I'm just going to use a math mix pop to kind of create the logic for, am I near a neighbor? Has a collision happened? Should I be doing something? The way I'm going to do that is basically by checking the neighbor's ID. So if their ID is this number, we don't have a neighbor, no collision has happened. If the ID is anything less than that number, there is a collision and we should be doing something. So I'm just going to check, is something less than something else? In this case is A less than B. A is going to be our neighbor's ID, and B is going to just be that number that our neighbor should never be. So 42949672295. So in the case that our neighbor's ID is lower than this number, we can say that a collision has happened. So great, now we've got a column here that can measure collisions. Perfect. So what should we do next when a collision has occurred? Just for the sake of this tutorial, I'm going to go a little overboard with the math mix here in a second. There's probably more optimal ways to do this or ways to do it a little bit neater and more clean, but just to really turn what I'm saying in English into some runnable program here, I'm going to use another math mix, which is going to have a whole lot of operations. So please try your best to follow along. What I'm going to do is make an attribute for myself. I'm going to make an attribute for if I am rock, if I am paper, or if I am scissors. And I'm going to do the same thing for my neighbors. So the way I'm going to do that is a whole bunch of if A is equal to B statements. So if my state is equal to 0, then I know that I am paper, and I'm just going to say self is paper. SIP is going to be our new column for that, our new attribute. Self is paper. And I'm going to do this a lot. If A equals B, If my state is 1, then self is scissors. I'm going to do another one. If A is equal to B, if state is 2, then self is rock, SIR. So I've got 3 new attributes here for self is paper, self is rock, self is scissors. And let me just make sure that this is running right. My state is 0. So yes, I am paper. Is everything paper? Yeah, okay, everything's paper. How did that happen? I'm going to press 1 again. Okay. And now everything should be different. And self is paper. Yeah, great. Okay. So there's some variation in the self is paper here. Okay. Anyways, now we're going to make one for all of our neighbors. I'm going to check if my nearest neighbor, if their state, right? Not the neighbor themselves, but if the nearest neighbor's state is equal to 0, then neighbor is paper. I'll do another one. Comparing A to B, if the neighbor's state is 1, then that means that my neighbor is scissors. And if I do one last check here, A is equal to B, then I will say my neighbor's state 2. That means my neighbor is a rock. Okay, so by now I've got a ton of attributes, and I don't think there's any harm, at least right now, in having this many attributes, but it's just kind of good to have them so that we can do some interesting math with them in a second here. We've got a collection here of our self versus our neighbor. Now what we want to do is we want to say if I am different from my neighbor, I should change to become my neighbor. The way we're going to do that, you can kind of think about this as an and operation when we talk about logic. So let me see if I can kind of draw out a logic table here. So if we think about a truth table, we have argument 1, argument 2, and then the result. Okay, if both inputs are false or if both of them are 0, the result is 0. If one of them is true and the other one is false, the result is 0. Vice versa. If both of them are true, then the result is 1. And this is how we create an and statement. Now, another way that you can think about this to get these results is if you just multiply the first input by the second input. So 0 times 0 is equal to 0. 0 times 1 is 0. But 1 times 1 is 1. What that means is if we need to change, become our neighbor or something, then that means that we need to be something and our neighbor also needs to be something else. So let's make a very, very specific check for what we are and what our neighbor is. In the case that we bump into our neighbor and we are, and I'm just going to do the A times B operation, our neighbor is paper, but we, self, is rock. Well, paper covers rock. So the result of that is that we need to change to paper. I'm going to make another statement that's quite similar to that one. I'm going to say, in the case that our neighbor is scissors, but we ourselves, self is paper, well then we need to change to scissors because scissors cuts paper. And we'll do a third one. Again, A times B. We have one for neighbor is paper, one for neighbor is scissors. So last one is going to be if our neighbor is rock, well, rock beat scissors. So if neighbor is rock and self is scissors, then we need to change to rock. CTR, CTS, and CTP are our kind of variables or our attributes that are going to tell us if we need to change into something. Let's take a moment to look at another type of logic table. So I'm going to write down the logic table for an OR statement. If A is 0 and B is 0, the result of OR is 0. If A is 1 and B is 0, the result of OR is 1. Vice versa is also 1, and 1 and 1 makes 1 for an OR statement. Another way you can think about this, if you make the maximum number 1, you can think about this as A plus B gives you OR. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1. In the case of 1 plus 1, we get 2, but we just know that it's not 0, so we can just pretend it's 1. This is basically addition. So what we want to do is we want to check, is there something for us to do? Do we need to change into something? So in that case, we're going to make an A plus B plus C statement. If we are supposed to change to paper, or if we're supposed to change to rock, or if we are supposed to change to scissors, then the result is that we should be changing to our neighbor. And this is going to be the attribute that we use from this very long list of attributes now that we have. This is our attribute that tells us it's time to become whatever our neighbor is. Now, it's possible that in some cases, say if we pause this, right? In the case we don't have a nearest neighbor, it still evaluates that our nearest neighbor is paper. Because there are some times where a collision has not happened, right? And our collision is defined by, is there a neighbor that is near us? We need to make a check. First of all, do we have the instruction to become our neighbor? And 2, is there actually a neighbor near us? So we're going to add another math mix here. This math mix is just going to do a little logic check for us. And it's the same as before in terms of creating an AND statement. To make an AND statement, we say A times B. And in this case, we want to make sure that there is a collision and that there is a instruction to change to our neighbor. If that is the case, let's just say that now we truly can direct ourselves to change to our neighbor. So since this is happening before we hit the end of the feedback loop, it's like we find out whether or not we should become our neighbor. We verify, we double check that we should become our neighbor. And then we can include the logic here to actually become our neighbor before this feedback loop continues and iterates through every cycle. So hopefully you're able to kind of follow that. If I demonstrate it, the video may derail quite a bit. So this is just our check to make sure we really, really should become our neighbor. And then finally, to actually become our neighbor, we're going to use one last math mix here. And this guy is just going to say if, right? If we use if statements, we want to use A, if C, else B. In this case, we're checking to see if we are supposed to change to neighbor, then our state should be whatever our neighbor's state is. Otherwise, it's just whatever our current state is. So when I give this a play, we see now that Papers colliding with rocks turn the rocks into paper. Scissors colliding with papers turn them into scissors. And then rocks colliding with scissors will turn them into rocks, but I think we didn't see any of those before scissors took over. In essence, this is mostly the network that we're working with. Right? We can keep on resetting it, but there are a couple other things we can do to make this network just do more stuff for the sake of learning how pops work. So one thing that I think would be kind of cool is if one of these pops changes into its neighbor, I think it'd be good if it changed its direction. Maybe it bounces off the neighbor, or maybe it inverts its current direction or something like that. So what we can do is in the final check where we are changing the state, in the case that the state has been changed, we can also just throw in an operation right afterwards that says if it has become its neighbor, then set its velocity to the inverted velocity. So we'll just use the same logic that we've already been using for that. If we've been told to change to neighbor, then the result is that the velocity of x should become the inverted velocity of x. And I forget what that was, but here I think it's inverted vel x. Otherwise, if it didn't collide with its neighbor, then it should just use the velocity it already had. So I'll just reset this. So hopefully we can see now that sometimes when they bump into each other, they change directions. And to be more thorough, we'll just do it in the y direction as well, using the same logic. If it has been told to change into its neighbor, then its velocity in y should also change to the inverted y velocity. Otherwise, use the regular y velocity that it already had. So it's kind of like if it hits a neighbor, pretend that the neighbor was a wall for a second and bounce. So I'll reset this, and we should see a lot more bouncing activity going on. Now, another thing you'll probably notice is that when I press 1 here, right, when I reset this, it doesn't really seem like all of these scissors and papers and rocks were randomly placed. It seems like they kind of are following a uniform pattern again. And that is a result of these random generations and these seeds. I've got 4 different randoms here, and all of them kind of have the same seed. So I'm just going to change this seed to 3 and this seed to 4. But now I also get the problem where every time I reset, I keep getting the exact same kind of randomized starting position, and it's not unique every single time. So one thing to kind of make that change every single time you start this feedback loop, because keep in mind, the feedback is literally just taking a screenshot of the starting conditions and then deciding to add movement to it through the use of, velocity and stuff like that. If I tell these randoms to change their seed every single frame, for example, random 1 changes its seed to abs time dot frames, abs time dot frame. Random 2 can do the same thing, abs time dot frame, but since we don't want it to be the same as the first one, we'll do frame plus 1. Same thing over here. This random 3 can be abs time dot frame plus 2, and this final random can be abs time dot frame plus 3. Now all of them are going to have random seeds. So every time I press 1 and recreate this network, all of the points will have different kind of starting positions. We'll see different distributions of scissors and rocks and stuff like that. Cool. So now we can kind of always have this changing network where it's exciting to watch, and we can pick a team, whichever one we think is going to win this ultimate game of rock, paper, scissors. And if we want to scale up the number of points even more, say from 50 of them to maybe 200, we can easily do that here in the very first random. Now that the starting number of points has been set to 200, I just pulse the feedback loop, and now we've got 200 rock, papers, and scissors to root for. And it looks like scissors might be winning this one. If we want the icons to be smaller, maybe they're too large and they're overlapping each other, we can of course just go to the rectangles and then change their size to be smaller. But now it's possible that maybe their collision is too far away or too close or something. Like let's say I make them way too small and they're bumping into things that they haven't even hit yet. That's where I can go to the neighbor pop here and adjust whatever the distance is. That should be the maximum distance for them to detect a collision. So I can make it so that the distance is like really, really far away so that they bump into things that they're not even near. Or I can make the distance really, really small so that they basically have to be on top of another icon before it will register any kind of a collision. So that's just how you can play around with the size of your textures, and you can play around with the size of the collision distance as well to make that properly fit. Okay, now one of the last things that's good to use from this network to just kind of analyze, for example, the number of scissors versus the number of rocks versus the number of papers, is a set of chops. This part is a pretty old school TouchDesigner. So from this, actually from the states here, we can actually just use the states themselves and we can connect them to 3 logic chops. So first I'm going to connect to a logic 1. I'll turn time slicing off. And this logic, I'll set the operation to be off when it's outside of bounds. So we know that the states of these pops are always going to be 0 or a 1 or a 2. So what I want is basically for this first logic to tell me whenever there are zeros. I'll copy and paste, and this guy should tell me whenever there are 1s. And I'll copy and paste one more time, and then this one should tell me whenever there are 2s. And if I reset, we should see that these numbers are all flashing, but eventually when one of these conforms and wins the race, like I think, oh, who's going to do it? Is it going to be scissors? Is it going to be rock? It looks like it might be rock. Nope, paper's making a comeback. Okay, so most of them are rocks at this point, and now most of them are paper. So it looks like here we go. All the scissors died out, and a majority of them are all state 0. So the papers won this one. So if I go here to analyze after the logic, and I calculate the sum of all the cases where it is a 1, then I see that there are 200 instances of state 0. If I use the same analyze for state 1, the scissors, I have 0. If I do the same thing for state 2, I have 0 rocks. Right, I can basically use this to create some text. If I connect this to a null all the way at the end of the network, I just call this BG for background. And then in the middle here, I insert a text operator. I can write something down like, let's just make it some raw code. So I'll just write down the number of papers is going to be whatever this value is. In fact, it's probably easier to just make this a chop reference. So I will drag and drop this as a chop reference. I will first typecast it as an integer. So it's just 200 instead of 200.0. Then I will turn it into a string, and then I will say that we have papers plus that string, And now we have a live counter here that tells me how many papers there are. I can move it all the way to the left, and I can move it up to the top left of the screen. And then when I reset this, we can see a live counter for how many papers there are. I'll basically just do the exact same thing one more time. But instead of papers this time, it will be scissors. I will move the text down a little bit. And then to reference how many scissors there are, this should be looking at not analyze 1, but analyze 2. So analyze 2 will tell me that there are 0 scissors because rocks look like they won this battle. But if I reset, now we see that the numbers are different. And then lastly, I'm just gonna, just copy and paste the same text and do the same thing for rocks. So rocks are going to be reading from analyze 3. Instead of scissors, they're going to say rock. And then I will move the font down a little bit. So we see that scissors won this battle, and I can reset. And then we have kind of like a live counter for who's in the lead. So yeah, in essence, that is basically the network. I'll just make the size of these scissors, or the size of the icons, a little bit larger. Maybe we don't need so many instances, so we'll just bring it down to 60 pops or something like that. Reset the feedback loop, and why don't we just add a RGB key here in the background so we can give it a black background. I hope you learned something from this video. I hope you had a chance to kind of explore the way that we can think about pops from the perspective of designing a feedback loop, deciding what kinds of attributes would be good to create before the feedback loop, and then jumping back into the feedback loop, making use of the pop2dat to kind of troubleshoot and read your values. And maybe you even learned something here regarding using logics and other old school TouchDesigner operators to create texture instancing networks and to calculate the number of pops that fit a certain criteria. But anyways, if you have any questions about the project file, feel free to message me directly or leave a comment. And I hope you enjoy your educational journey with pops.